Okay, welcome back to part 3 of this video series. So in the previous parts, what we did was that I gave you the circuit, and then I told you to come up with the SOP expression. And then the second part was that I gave you the SOP, and then I told you to draw the circuit. All right, so that was part 1, and this was part 2. And today, in part 3, what I'm going to do is I'm going to teach you to see whether this or this can be simplified. Now, what do I mean by this? Okay, so open up your textbooks. So let's say I have this SOP expression, all right? Okay, let's say you worked it out from the truth table and so on and so forth. So you got this SOP expression, and then I ask you to build this circuit, okay? So X is true if this or this or this happens, all right? So being the very faithful and studious students that you are, you manage to draw out this circuit, and then you manage to implement this circuit. Okay, well and good. Congratulations. Good for you. But wouldn't it be great? Wouldn't it be great if we can take this expression over here and simplify it to this expression? Wouldn't it be great? And wouldn't it be great, since that now this is a much simpler expression, to implement the solution instead of drawing this and putting all this on the breadboard? It would be just these 3 gates. Wouldn't that be great? It would be. Yes, it would. And I'm going to teach you how to do it. So pay attention and let's go. Boom. All right, so these are the steps, right? The first thing is that to simplify, we need to draw something called a KMap. K stands for Kano. It's some really smart genius dude, and we honor him by using his name, Kano map. Short, KMap. Sounds cool. Now, if it's a 2-input system, you draw a 4-box square. Okay, A, B, 0, 1, 0, 1. If it's a 3-input system, we need to draw a 8-box rectangle. Okay, A, B, C, or D, E, F, or whatever the alphabets you're using. Now, so this is the weird thing about the KMap, right? You have to label 0, 0, 0, 1. Now, I know it's 0, 0, 0, 1, 1, 0, 1, 1. But in this case, the KMap, please stick to this convention of 0, 0, 0, 1, 1, 1, then 1, 0. Okay? This one is just 0, 1. Don't ask me why. Just do it. It works this way. Okay. So first of all, you have to remember the KMap convention. Okay. Now, I don't think we are going to be so kind, or Cambridge is going to be so kind to give you a 2-input solution. So more or less try and get used to a 3-input solution. Okay. So remember this: 0, 0, 0, 1, 1, 1, 1, 0. Remember this. After that, we need to populate this KMap. Okay, so we need to fill in these holes. So if this is A, B, C, 0, 0, 0. So we look at your truth table, 0, 0, 0. Whatever number this is, we put it in this box. What about the second box? 0, 0, 1. So let's look for 0, 0, 1. Whatever number this is, we put into the second box, so on and so forth. Okay, and after that, whatever ones that we get in the KMap, we need to do something called looping. So we need to loop the ones together. Now, we loop in the ones in groups of 1 or 4. Do not loop in 3. 3 is just weird. Don't do a 3. Okay, 1, 2, or 4. Remember that. So how do we loop in 4? If there are 4 in a row, you can loop them 4. If there are 4 in a box, loop them 4. Now this is the cool thing, right? If I have 2 ones and 2 ones at the start and the end, you can actually loop them together, sort of like wrapping it from the start to the end like this. So you can loop them like this. Loop them in 2. So 2, 2, 2, 2, and you can do the start to the end here. Okay, can loop them. And loop in 1. So let's say you don't have a choice, you only have 1, 1, so no choice, just loop in 1. right? 1, 1, 1, 1. You this, there's no diagonal loops here. Diagonal loops are not allowed. No, no. So loop them in this case in ones. Now the whole idea is that the bigger the loop, the better it is, because the bigger the loop, the more simple your expression will be. Okay, so in this case, yeah, bigger is better. All right. So also you can double loop. What do I mean by that? So you would imagine, oh, I already looped this fella, so this poor little fella has to be alone. Actually, no, you can re-loop this one. So this one loop or pair is actually a better method than looping this and this. Okay, remember, the bigger the loop, the simpler your expression will be. Go big or go home. All right. So in this case, same thing. Oh, you can loop here, or you can. You're not wrong if you do that. It's just that it won't be as simple as it could be. So a better idea is to loop this too. But there is an even better idea. You can actually do the loop from the start to the end. Okay, so there are many different methods of looping. You just have to practice more and kind of figure out the most efficient and best way to loop. Remember, I bring this theory back, the bigger the better. Size matters. Okay? Okay, so after we loop it, we need to come up with the SOP expression. So let's say it's loop in one square here, a pair from the start to end here. Okay, so let's do the now in. So what we want to do is that we want to see when we go from this one to this one, which input doesn't change. We want to keep the one that doesn't change. So in this case, B is common. B doesn't change. The B is common. So we want a common one. B is common. Okay, C changes from 0 to 1. We don't want the C in that case. So from top to bottom, A changes. So we also don't want A. We want the one that does not change, the common one amongst all four. So the common one amongst all four is B. But in this case, it's the 0 of the B. So therefore, it is the B complement. Now, then we go on to the second loop, right? The start to the end. So A is common, right? Between this one and this one, A doesn't change. A is common, it's always 1, no matter whether you go from here to here or here from here, A is still 1. B changes from 0 to 1, so I don't want B. C is common, C doesn't change, it's still a 0 here, so I want C. C zeros, that means element. So between this and this, when I travel from here back to the loop, the only two things that don't change is A1, okay? So therefore it's A and C complement. And then since I have two loops, right, it can be either B complement or A and C complement. Okay, can? So this is another example. Let's give this a try here. Let's give this a try. So this is already the truth table drawn out for you, and they want you to populate the KMap. So first of all, you have to set up the KMap, right? So if without simplifying, this would be the SOP Boolean expression. Very complicated. So let's see whether we can simplify it. Okay, so 0, 0, 0. Let's look for 0, 0, 0. The output is 1. So let's put a 1 here. 0, 0, 1. 0, 0, 1. It is 1. 0, 1, 1. So 0, 1, 1. It is 0. 0, 1, 0. 0, 1, 0. It is 0. Next, we go on to 100. 100 is 1. 101. 101 is 0. 111. 111 is 0. And 110110 is 0. Like so. Okay, so we've filled in the KMap. Right? Now we need to do our looping. So let's do some loops. So remember, we can loop in pairs. So let's do one loop here. And of course, let's use another color. We can do a second loop here. So we're going to have 2 loops here. Okay, so the output, what's the output? The output is x. Okay, so x, let's do this loop first. Okay, so a is not common. Okay, between these two, between the a is 0 and 1, so it's not common. I don't want a is bad. The b complement and c complement is common here, so I do need both b and c. Yeah, so this is needed. So in this case, is b complement and c complement. Okay, or because I've another loop, in this case a 0 doesn't change. A is common for these two, so I want a common because it's the 0 of the a that doesn't change, right? Then I compare this when I move from here to here between these two. Which one is common? It seems that the b stays the same. The c changes from a 0 to a 1. So I don't want the c. I want the one that is common, stays the same. So it is the b complement, like so. Okay, so this is how I fill in the KMap and then derive the simplified SOP. Now, wouldn't you say this is so much simpler compared to this? I would say so. Okay, so the next few chapters, the next few pages just kind of shows you how I derive the answer. You can go read it. What I do want you to do right now is to try simplifying your own, coming out of your own KMap like this. Okay, make sure that you can simplify this to this. And tell you what, I'm going to do this for you, and then you check your answer. You pause right now, and when you're done, check back in, start play. So hopefully you've tried question 2, 1, 2, 3. I've kind of worked out the solution for question 2 and 3. So this is the KMap I drew for this expression, and by looping these two ones, I am able that this is the expression that I will get. Okay, so hopefully you managed to do this KMap. And for number 3, the KMap that I got from this expression is this. And because there is a very nice loop of 4, the only common one amongst all 4 ones is that b always remains 1 no matter which of the ones you go to. So x is just b. Boom, just like that. From this very long complicated expression, I can simplify it to just b. Okay, so the simplification using KMax is very useful. The next chapter, or the next subchapter, is simplifying a logic circuit using Boolean algebra. Now, for your O-level syllabus, you either need to use KMap or Boolean algebra. For me, I personally think KMaps are so much easier, so I'm just going to teach you the simplification method using KMaps. But if you're interested in Boolean algebra, please read on yourself, okay? So I'll only make the video series on simplification using KMaps. Go and practice more of it in your worksheets. There are lots of online examples. Go and practice them, okay? Once again, if you're not sure, please look for me in class. So there is one more part, and I'll see you soon.